All right, we're going to look at polynomial functions. And we have already looked at some polynomial functions. We looked at lines and constant functions, which are horizontal lines, oblique lines. We looked at those. We looked at quadratics, which are second-degree polynomials. So let me kind of give a really generic version of the form of a polynomial function. So you have x to some number, and then its coefficient, and then you have, the next lowest power and its coefficient, and so on until you get down to x squared and x, and then the constant term. And so we've done problems based in these. Now we're going to look at what if it's x cubed, what if it's x fourth, so on. So let me describe some things in this statement. Here we have a leading term, and the leading term is the one with the highest power. So in my kind of generic version here, it would be this xn, a sub n, x to the n. We also have a constant term, and the constant term is this a sub 0, this term without a variable on it. And any of these coefficients could be 0 in here. So you could have like x to the 5th, but not an x to the 4th because its coefficient is 0, and so on. All right, so these are going to tell us stuff about the graph based on these two terms, this leading term and this constant term. Think about if this was written in the correct order, the first term and the last term. All right, so what does the leading term tell us? It tells us if the leading coefficient and that's just the coefficient of the leading term, so a sub n. If this is positive, then the graph rises on the right-hand side. If it's negative, then the graph falls on the right-hand side. So you can think about if you had a line with a positive slope, on the right-hand side it's going up, or if you had a positive x squared, that would be going up. Likewise, if you had a negative slope, your line's going down on the right, or if you had a negative x squared, your parabola is going down. And so those statements aren't true just for lines and parabolas, but it's true for all polynomials. Okay. Let's see some other things. So we have what we call the degree, and using my notation back here, the degree is this highest power on that leading term. That's how you know it's a leading term, because it has highest power. And this tells you several kind of different things. So one thing it tells you is if the degree is even, so x squared, x to the 4th, x to the 6th, then the left side matches the right. And what I mean by that is if the graph is going up on the right-hand side, then it's got to also be going up on the left-hand side. Likewise, if it's going down on the right-hand side, it's also going to be going down on the left-hand side. So that's what I mean by it has to match. So, if I see a graph that looks kind of like this, I know the highest power has to be, an even number, x to the 4th, x to the 6th, x to the 8th, something like that. Likewise, if the degree is odd, then the left side is the opposite of the right side. Okay, so you get something that looks like this, up on the right, down on the left, or something that looks like this, down on the right, up on the left. Those would be odd functions, odd degrees. So that's something they tell you. Another thing it tells you, the maximum number of x-intercepts. So if I saw something and it looked like this, and I said, could this be x to the fourth? And the answer is no, it can't be x to the fourth. The reason why is because it's got 1, 2, 3, 4, 5, 6. So it's got to be at least x to the 6th. It could even be higher. It could be x to the 8th, x to the 10th, whatever. But it's got to be at least x to the 6th. So that's something the degree tells you, is how many maximum x-intercepts. You can always have less than this, but you can't have more than the degree. Another thing that's kind of related to that is this tells, if you take the degree n minus, and you subtract 1 from it, this is the maximum number of terms. So I said this could be x to the 6th. You can think there's 1, 2, 3, 4, 5 turns in there. So you think if this was x to the 6th, then 6 minus 1 would say 5. There could possibly be 5 turns. And again, you might not have that many. If you think about x to the 4th, its most basic form, it looks very much like a parabola. It's just a little steeper, and it only has 1 turn. So just because you have x to the 4th doesn't mean you're going to have 3 turns. It just says you can't have more than 3 turns and be x to the 4th. Okay, so that's something it tells you. The constant, this constant term, a sub 0, right? The number at the end of our statement without a letter. What does it tell us? Well, the constant is the y-coordinate of the y-intercept. So y-intercept is going to be a comma a sub 0. You think about, for a line y equals mx plus b, that's the y value of the y-intercept, 0 comma b. If you had a parabola quadratic function written out in the general form, then 0 comma c is the y-intercept. So whatever the constant term is, that's the y-intercept. That's where it's going to hit the y-axis at. So if you don't see one of those, that must mean it goes through the origin. All polynomial functions have a y-intercept. Not all of them have x-intercepts. They all have y-intercepts. All right. So I need to talk about x-intercepts, but I'm going to go ahead and zeros. I'm going to do that while I'm talking about, let's draw some pictures of graphs. So let's say I want to graph the polynomial function f of x equals x cubed minus 5x squared minus 4x plus 20. So I want to graph that. So what I want you to do is I want to figure out what are the right and left hand behaviors, up or down. I want to find the y-intercept, if there is one. Well, there always is one, so I want to find it. And I want to find any x-intercepts. And then kind of one thing you will occasionally do is find the vertex. But this is only for quadratics. So if it's not a quadratic, You don't worry about the vertex. And the fact that this highest power is x to the third means this is not a quadratic. And something that's a quadratic is a second degree polynomial. So the highest power is 2. So it doesn't matter how many terms there are. It doesn't matter what shape it is. It might look kind of like a quadratic, and that might allow you to use the quadratic formula to do some things. But if it's not a second degree polynomial, you can't find the vertex. To find these turnaround spots that I talked about on this, to find those turnaround spots, what you would need to do is do calculus. And we're not going to get into that. So the only time we can find the turnaround spot would be on a quadratic. All right, so let's go through this and find out as much as this we can find. So looking at this, here's the highest power term. And I notice the sign in front is positive. So that tells me on the right-hand side, it's going up. So I always figure out what it does on the right-hand side first. Then I look at the power, and I see x cubed. What that's telling me is that the left hand does the opposite of whatever the right hand does. So since the right hand is going up, the left hand must be going down. If this is an odd power, these two are always opposites of each other. All right. To find the y-intercept, how we find the y-intercept is how we always find the y-intercept. We put 0 in for all of our x's. So x cubed disappears, x squared disappears, x disappears, and we get 20. We get this constant value, so 0, 20. So notice I haven't really done any work yet. Just by looking at this equation, I can figure out these first few things. Now to find the x-intercepts, if this isn't already factored for me, I'm going to have to do a little bit of work to figure out what these are. So to find the x-intercept, I want to make y0 or f of x. So I'm going to set this equal to 0 and solve it. So this is 4 terms. So I'm going to factor this by grouping. X squared, x minus 5. We've got to get an x minus 5 over here. So that means I have to factor out a -4. -4 times -5 is positive 20, so that's going to work. I'm going to take out my x minus 5. That's going to leave me with x squared minus 4. And then I can factor that as the difference of squares. X minus 2, x plus 2. So these are the factors. I set each one of these equal to 0, and I get positive 5, positive 2, and negative 2, and these are the zeros, the real zeros. Soon, like right after spring break, we'll talk about, or wherever we are in the semester, in a few weeks, we're going to talk about all zeros. We're going to start working on imaginary numbers, but at this point, we're just dealing with real zeros. All right, so what does that tell me? Well, those are the x values of the x-intercepts. So 5, 0, 2, 0, and -2, 0. Now with these, I could draw a picture of this graph. So let's say I have y-intercept. Oh, let's back that up. Okay. Got the really high y-intercept. So I'm going to count this by 5, 10, 15, 20. There's a y-intercept at 0, 20. What do I know? I know it's going up over here, down over here. I have something over here. You don't have to scale your x and y axis the same. Just when you're drawing lines, often if you want to use the slope easily, you do scale them the same. But other than that, you usually don't worry about it if they're not scaled the same. So this is 5 here. All right, so what is this going to do? It's going to start down here. It's going to go through. I go up here, come down here, come back up, and then head out. And there we go. And I'm guessing if you plug that into a graphing utility, this equation, you get something, pretty close to that. I mean, we're not trying to be super exact. We're just trying to remember, we're not finding where it actually turns around at. We're just estimating that because we would need to do calculus to figure out those spots, and we're not going to do that. All right, so let's do another one of these. Let's say I wanted to graph g of x equals -2 x times x minus 1 squared times x plus 4 cubed. Okay, so in this case, this is a little bit harder to do, figure out what's on the right and left and the y-intercept because it's not in that, that general form, that multiplied out form. So first thing I want to do, remember, I want to know what's happening at the front and what's happening at the back. That's what tells me these things. So at the front, the way you can figure that out with any kind of polynomial expression, assuming everyone's in the correct order, in these parentheses, you just take first times first times first times first times first times first, and that'll give you the first term. So I'm going to take negative 2x times another x, because it's squared, times another x times another x times another x, because it's cubed. So 3x's times 2x's times another x times a negative 2, that's going to be negative 2x to the 6. And then it's going to have, some other terms there, x to the 5th, x to the 4th, whatever. But this is telling me on the right-hand side, it's going down. And the fact that this is x to the 6, that's an even power, the left-hand side is going to match. So anytime the power is even, that highest power term is even, then it's always going to be matching left and right. So up and up or down and down. All right, to find the y-intercept, you could just plug in 0 here, or again, it's the constant term, so you could think that's the last term. So just like how you can multiply first times first times first times first, you can multiply last times last times last times last, here. So if I multiply 4 to the third times negative 1 squared, 1, times negative 2x, I'm going to get negative 128x, which is not the last term. What is the last term? Well, it must be 0, which if you make all these x's 0, negative 2 times 0 times stuff, well, 0 times anything is 0. So yeah, 0, 0 is a y-intercept. Now I want to find my x-intercepts. Okay. So what I'm going to do is, again, I'm going to set this thing equal to 0, and I'm going to set each factor equal to 0, and I'm going to get, it's already factored for me, right? This is already in its factored form. So I'm going to say, okay, what are my zeros? My zeros are x equals, well, 0. We just found out that if you make x equals 0, you get an answer of 0, so that's a 0. Positive 1 is a 0, and negative 4. Negative 4 is a 0. So my x-intercepts are 0, 0, 1, 0, and negative 4, 0. And now I'm ready to start drawing this picture. So, back that up, and I can make that a little straighter. A little straighter. So 0, 0, there's my y-intercept, and it's going down and down. Just putting these. Don't try to connect these little arrows. These are just kind of reminder arrows when you're drawing your picture. So let's see, 1, 2, 3, 4, negative 4, 0, 0, positive 1. So what does this look like? And it looks like the following. It's going to look like, let me erase that. Just so hard thinking about this, and I'm not drawing it very, very curvy. Like something like that. And again, you can put that in a graphing calculator and see what that looks like, but you're going to get something kind of similar. I'm just making it worse. Kind of similar to this. All right. There you go. Basically, it's going to cross that negative 4. It's going to, oh, no, I messed up. We need to erase all that. I messed the picture up. Let's try it again. Okay. Sorry about that. Erase everything I've ever talked about from your memory, and let's try it again. Negative 4, 1, 2, 3, 4, boom, 0, 0, and positive 1. Okay. So let's try that again. This actually looks more like that. Okay. So that's kind of how I messed that up there. something like that. All right, so let me explain how I knew it looked like that. Because if you're looking at 3 dots, you may wonder, how did I know it was going to do that? And the way I know is if I come back up here and I say, okay, where did I get this -4 from? Well, I got it from this, and there are actually 3 of those. There is a -4, and another, so there's 3 -4 intercepts here. 0, 0, 0. And then when I looked at this 0, 0, there was, where did this come from? Where it came from this, where there's only one of those. So there's only 1, 0, 0. And then when I look at where'd that 1 come from, well, there was actually 2 of those. So, I got 1, 0, and another 1, 0. Well, that's significant because that's telling me something about the graph. Notice this happened once, this happened 3 times. Those are both odd number of occurrences. The graph crosses the x-axis at an odd number of occurrences for that x-intercept, or that 0. On the other hand, this 1 happened twice. That's an even number of times. So if it happens an even number of times, the graph bounces. So if a 0 or x-intercept, since at this point, when we're dealing with real ones, they're they occur the same number of times. So if a 0 and an x-intercept occur an odd number of times, what we do is we cross. We cross when we intersect that axis. And if it occurs an even number of times, we bounce, or we just intersect and we don't cross. So that's always true with those zeros. And that tells you something. If you remember when we did those critical value tests, and you say -4 is a critical value, and 0 is a critical value, and 1 is a critical value. And we said, oh, when this was an even number of times, you got like same, right? But when this occurred an odd number of times, even if it occurred, these are different. You get different results. It might be work, don't work, back to working and then working, or working, don't work, work, however it happened. So when it happened an even number of times, they matched, and when it happened an odd number of times, they were different from each other. So all right, let's talk about then writing equations. So this is kind of like a little reverse of what we were just talking about with finding zeros and things. So let's say we want to find a 3rd degree polynomial function with x-intercepts at 2, 0, 1/2, 0, and -4, 0. Okay? So we got 3 of them. That's good because we want a 3rd degree polynomial. So, we're going to have 1 for each factor. So what we know is that the zeros are x equals 2, x equals 1/2, x equals -4. Subtract 2, so x minus 2 equals 0. Subtract 1/2. So x minus 1/2 equals 0, and then add 4, so x plus 4 equals 0. And again, if you don't like working with fractions, maybe you multiply this one on both sides by the denominator, so you get 2x minus 1 equals 0, and these are our factors. And what we're going to do is we're going to say y equals these factors multiplied together. And if we're going to multiply this out, then just remember that we're going to multiply three things out. You want to multiply two of them together, get an answer, multiply that by the third one. So if I multiply these first two together, I'm going to get, what, x squared. Outside pair is negative x, inside pair is negative 4x. So a negative x and a negative 4x make it negative 5x. And then, oh, this should be a 2x squared. And then negative 2 times negative 1, positive 2. And then I'm going to multiply that by x plus 4. And I'm going to distribute this x plus 4 into the trinomial. So 2x cubed minus 5x squared plus 2x. And then I'm going to distribute the 4 through. That's going to be a positive 8x squared, a negative 20x, and a positive 8. So my function could look like the following: 2x cubed plus 3x squared minus 18x plus 8. Which is fine, you know. But the thing is, this is not the only, this is just a third-degree polynomial function. In order to find the exact polynomial function, I would need another point because I might have some kind of multiplier involved here. And so since I don't know what that multiplier could be at this point, because I don't have enough information, I would need more information here, I can't actually finish this problem. So let's look at a problem where I want to find what this multiplier is. So what would that look like? So I'm going to change the directions here a little bit. I'm going to say find the, and we'll just say, so this is a now we're going to find the actual equation. So I'm going to have to give you a little bit more information. Find the third degree polynomial function with x-intercepts we're going to say 0, 0, 2, 0, and negative 3, 0, and going through, and now here's that information I need, 1, 5. Okay. So since we know the x-intercepts, we know the zeros are x equals 0, x equals 2, and x equals negative 3. Notice I'm not using this 1, 5 yet. That's not an x-intercept, so that has nothing to do with the factors or the zeros. So I'm going to subtract 2. So x minus 2 is equal to 0. Notice this is already equal to 0, so I don't have to do anything to that. Add 3. X plus 3 equals 0. And so these are my factors. So now I'm ready to start trying to write my equation. My equation is going to be y equals, I'm going to have an x as a multiplier. I'm going to have x minus 2 as a multiplier, and I'm going to have x plus 3 as one of my factors here. And then I'm going to have something else, some other number. And I don't know what that number is. And that's where this point is going to come in handy. Because without that point, I couldn't figure this out. But with this point, this is telling me when x is 1, y is 5. So when all my x's are 1, my y is 5. So I'm going to go into my formula that I've constructed so far, and I'm going to change all the x's to 1. So this is going to be 1 minus 2, and 1 plus 3. And so 1, this is going to be a negative 1, that's going to be a positive 4. So it looks like 1 times negative 1 times 4 is a negative 4. So negative 4 times a, divide both sides by negative 4. And so my equation is y equals negative 5 over 4. Oh, that should be, let's get rid of that. Okay, negative 5 over 4 x times x minus 2 times x plus 3. Now, you might wonder, should I multiply all this out? And this one wouldn't be that bad to multiply. I'd probably multiply these two first and then distribute the negative 5/4 over x. But since this type of problem has an additional complexity over when we were just looking for a third degree polynomial, and we didn't have to worry about that extra multiplier involved, I'm going to ask that you don't multiply these out, because if you multiply them out, it may throw off your answers if you don't do it correctly. And so it just might increase the complexity of the problem more than is really necessary. So when you're asked to find the, you know, polynomial, I'm just going to ask you to leave, at this point, just leave these all together and stop there. And then just, you know, that way I can say, oh yeah, you got the right multiplier and your factors are all set up correctly. So, you know, there's full credit. Whereas if you multiply this out and you made some little mistake, even though you did all this work correctly, now I got to mark you off. So, you know, just stop here. Don't multiply it all out. All right. So there's polynomial functions. There's